Hello, welcome to the fourth lecture in linear algebra series. In last lecture, we had discussed how to find eigenvalues. In this lecture, we will be discussing how to find eigenvectors and some important properties of the eigenvalues and a special theorem called a Cayley-Hamilton theorem, which is useful in finding A inverse and A squares, A cubes, so on, A power n's. Now, in the last lecture, we had discussed a characteristic equation, that is determinant of A minus lambda I, and equate it to 0. You can find the lambdas. The lambda is the eigenvalue. Once you know the eigenvalues, if you substitute that eigenvalue here, then it will be of the form some a ax equal to 0. That is a system of homogeneous linear equations. Now, one of the trivial solutions of the system of linear equations is 0, and the non-trivial solutions are non-zero vectors. So we are interested in finding those non-trivial solutions. Those non-trivial solutions are called eigenvectors. So let us suppose A is 2, 1, 1, 2, and then we got the eigenvalues as lambda 1, 3, and lambda 2 is 1, and substitute that in the original equation. This is actually Ax equal to lambda x. We are finding that x vector, that is A minus lambda I equal to lambda I into x equal to 0. So substitute lambda as 3, then we are going to get this minus 1, 1, 1, minus 1, x1, x2, 0, 0. So if you do this one row transformation, that is simply R2 as R2 plus R1, then we'll get 0, 0. In the second row we get a 0, 0. That means the rank of A is same as the rank of AB augmented matrix, and it is less than 2. So we have infinite solutions. So in fact, we get only one equation, that is x1 minus x1 plus x2 equal to 0. There are two identical equations. So x1 equal to xt. There are infinite solutions. All those infinite solutions of the form some c, c. And any non-zero c you can choose, either 1, 1, 2, 2, 3, 3, so on. Similarly, if you substitute lambda 2 equal to 1, again we get two identical equations, x1 equal to minus x2. Then if you choose some c, then it will be of the form minus c, c, or c minus c. So you can have minus 1, 1, minus 2, 1, or 1, minus 1, so on. Infinite solution exists for this case also. This is how one can find the eigenvectors. Now, some important properties of the eigenvalues. The sum of the eigenvalues is equal to the trace of the given matrix, that is A, the coefficient matrix that are A. As you know, the trace of the matrix is sum of the diagonal elements. Similarly, the product of the eigenvalues is equal to the determinant of the matrix. So a matrix is symmetric matrix if A transpose is equal to A. Now the eigenvalues of a symmetric matrix are always real numbers. Similarly, the eigenvalues of the lower triangular or upper triangular matrix are the elements of the main diagonal. So the matrix is a singular, that means that its determinant is 0, if and only if one of its eigenvalues is 0, because it is equal to the determinant. So the eigenvalues of A inverse are reciprocals of the eigenvalues. If you know the eigenvalues of A, you can find eigenvalues of A inverse without computing A inverse. Simply those are reciprocals of the eigenvalues of A. Similarly, if you know eigenvalues of A, you can find out eigenvalues of A power k by simply taking powers, the kth power of the eigenvalues of A. If C, similarly, for some constant C, A plus C into I if you know the eigenvalues of A, you can find the eigenvalues of A plus Ci. Those are nothing but lambda plus C. These are very useful properties which are helpful in finding eigenvalues simply. And the next important theorem is the Cayley-Hamilton theorem. So the theorem statement is every square matrix satisfies its own characteristic equation. If you recall, the characteristic equation is determinant of A minus lambda I equated to 0, and you get some equation in lambda. That is a characteristic equation. Every square matrix also satisfies that characteristic equation. Okay, and it is useful in finding the inverse and for computing higher powers of the given matrix, that is like a square, a cube, a power n. And so let us see with an example. First we will see an example verifying Cayley-Hamilton theorem and finding how it is useful for finding the A inverse. So as we know, the characteristic equation is just find a determinant of A minus lambda I and equate it to 0. Whatever the equation that you get in lambda. So for this example, you are going to get a lambda square minus 5 lambda minus 2 equal to 0. And as the statement says that every square matrix satisfies its own characteristic equation. So you will get A square minus 5i minus 2i, and if you substitute this for A square, you are going to get this, and if you do the calculation like A square minus 5a minus 2i, you are going to get zeros. So this matrix, whatever the given matrix, satisfies this Cayley-Hamilton theorem. Now how it can be useful to find the A inverse? Now just take this 2i to right side, and so let us suppose A inverse A inverse exists. So in that case, you multiply A inverse on the both sides, and we get A minus 5i equal to 2A inverse. Now from that you can find out the A inverse. A inverse is 1 by 2 into A minus 5i. Similarly, this can also be used to find higher powers of A. Now for that, what we do is we will find some A power n, some expression for A power n. So let us consider this characteristic equation from the last example. So if you consider 1, 2, 0, 3, then we will get lambda square minus 4 lambda plus 3 equal to 0. Now as we know that the matrix also satisfies that, that is A square minus 4a plus 3 equal to 0. Suppose this is from the polynomial theorem, polynomial division theorem. Suppose we have some lambda power n, which is divided by this, when you divide this lambda power n by this characteristic equation lambda square minus 4 lambda plus 3, then you get some quotient. Let us suppose that quotient is q lambda. Then we can write like this: lambda power n as some quotient into lambda square minus 4 lambda plus 3 plus remainder. So the remainder, as we are dividing by lambda square, we get a remainder in the lambdas. So a lambda plus b. So now we can solve the coefficients by using the eigenvalues. So simply take lambda as 1, then a into 1 plus b, then you get a plus b as 1, and if you take lambda as 3, then you will get 3 power n 3a plus b, because this characteristic equation satisfies this lambda 1 equal to lambda 3, you are going to get 0 there. So the lambda power n is effectively a lambda plus b. So, and by using the combination of this characteristic equation and a polynomial theorem, we can say that even the matrix also satisfies this equation. That means a power n is simply, we can write it as a into capital A plus b. So that's an important result that we are going to use here. This can be easily verified by repeatedly substituting this. Suppose you have lambda square equal to 4 lambda minus 3. Now for a lambda cube, we can say it as 4 lambda square minus 3 lambda. Now in place of lambda square, you can substitute 4 lambda minus 3. From that, you can get some linear form, something like a lambda plus 4 or a lambda plus b form. So if you do it for n times the transformation, you are going to get the same value, that is some a into bi. So where a is, we have calculated a and b. A is 3 power n minus 1 by 2 and b is 3 minus 3n by 2. So if you substitute those, you will get the matrix for a power n. So from that you can find out any a power, like a power 4 or a power 5 or a power 10 directly. So this is how one can apply the Cayley-Hamilton theorem to find higher powers of a given matrix. Thank you.